In this video, we are going to demonstrate how to use Wolfram Alpha to reproduce some of the analytical solution to the integrals we have encountered in previous module. In this video, the first integral we want to solve with Wolfram Alpha is a fractional function of minus 2x plus 4 divided by the product of a quadratic factor and a linear factor which appears twice. To begin with, I type integrate with a capital I, left square bracket, open bracket, minus 2x plus 4, close the bracket, slash to generate the fractional placeholder, type in the expression for the denominator. There are two terms in the denominator. Now there are two placeholders in the denominator. So I'm going to type shift caret 3 to generate a placeholder raised to the power of 3, and this is going to be x minus 1. I'm going to type in x shift caret 2 plus 1. So that is the integration I want to integrate, and the variables of integration is x. Close the right bracket. That generates the mathematical symbol for performing the indefinite integral. I'll press shift enter, wait for a while. So what you see here in the blue color highlight is the result of the integration. Comparing the results from Wolfram Alpha and example 15, the analytical results in both cases are the same. Next, we want to show how Wolfram Alpha can be used to cast the fractional function of the integrand can be cast into its sum of partial fractions. In order to provide instruction and paste us the expression of the fractional function into the input panel sum, simply type partial fractions. Press shift enter. Wait for a few seconds. Now you see on the screen the input panel. Wolfram Alpha has correctly interpreted my input, generate the partial fractions for the fractional function that I supplied. And this is just the result of the partial fractions produced by Wolfram Alpha. You can compare the partial fractions term by term. The expression of A, B, C, D in example 5 in the PowerPoint. You will find that Wolfram Alpha indeed reproduce this constant in the partial fractions correctly. In Wolfram Alpha, the term A has a value of 2 and the B here has a value of 1. The C term is a minus 2 and the D term is a value of 1. The next example we want to demonstrate is example 16, which is similar to example 15. So we define the fractional function in the input panel of the Wolfram Alpha. 1 over x to the power of 2 plus 1, and the whole thing would be placed in a bracket. Then I have an x multiplied with the term in the bracket to raise to the power of 2, and I have to be careful here. The x should be lying outside of the x squared plus 1 square term. Now I have finished defining the fractional function in example 16. To instruct Wolfram Alpha to give me the expression for the sum of its partial fraction, I simply type partial fraction. Whether there is an s or without an s, and whether there is a space between partial fraction and the expression, Wolfram Alpha was still able to interpret the input correctly. This shows the robustness of Wolfram Alpha in the sense that it is fault tolerant with respect to the input you key in. Here you can see that the input that I key in has been correctly interpreted by Wolfram Alpha, that it understood my request to cast the fractional function into its partial fractions. And the result is shown on the screen, which I highlighted in blue. This could be compared term by term against the expression as displayed in example 16 of the PowerPoint. Here, the values of the term A, which is the constant for the partial fraction 1 over x, is 1. The values of constant B in the partial fraction is minus 1. The constant C is 0 because there's no term corresponds to 1 over x squared plus 1. Constant d is minus 1 as correctly reproduced by Wolfram alpha, and there's no term of 1 over x squared plus 1 whole thing squared in the output of Wolfram alpha, which is consistent with the results in example 16 in the PowerPoint that the constant e is 0. Once we have shown how to cast the fractional function into its sum of partial fractions, we can then integrate this fractional function with respect to x. The result is as shown on the screen. We can compare the output from Wolfram alpha term by term with the result obtained in example 16 in the PowerPoint. They are exactly the same. Now let's try another example. Example 22, integrate the integral of 1 over square root of 4 plus x squared. So I type integrate open square bracket 1 over capital SQRT open left square bracket 4 plus x shift caret 2 close right bracket comma x close right bracket. Press shift enter. The result given by Wolfram alpha in the first instance is in the form of hyperbolic arc sine of x over 2. If you scroll down to check for alternative form of the integral, Wolfram alpha says the integral can also be expressed in terms of the log of the square root of x squared over 4 plus 1 plus half of x, which is exactly the same as the result expressed in example 22 in the PowerPoint. So Wolfram alpha has done a good job to reproduce the identical result for example 22. The next example is example 27, where the integration is not given by any standard integration technique we have discussed, but is obtained by using the integral table. Here we want to show that Wolfram alpha can produce a result in the integral table. Capital integrate open left square bracket 1 over x capital SQRT left square bracket 2x minus 4 close right square bracket comma x close right square bracket. That completes the definition of the integral. Press shift enter. So you can see that the integration result as produced by Wolfram alpha is exactly the same as the one shown in example 27 in the PowerPoint. The last example in this video we want to show is example 29. Again, an integral that could not be obtained by using standard integration techniques but have to be referred to the integral table. Capital integrate open square bracket left x times ARCSIN left open square bracket x close right square bracket. That generates the arc sine of x comma x close right bracket. Shift enter. Again, you find Wolfram alpha reproduces the indefinite integral as exactly as given in example 29 in the PowerPoint. From the last two examples we have just demonstrated, Wolfram alpha can play the role of integral table but with a much extended capability. The collections of integration results that could be produced by Wolfram alpha indeed is much larger than the collection of most ordinary integral table. As a conclusion to this video, I have attempted to give you a few more examples of how to use Wolfram alpha to reproduce some of the analytical expression of improper integration discussed in previous module. In the next video, I am going to demonstrate further the applications of Wolfram alpha to reproduce some of the improper integration results where Wolfram alpha is used to perform definite integration instead of indefinite ones.